Welcome you all. I am Dr. Smriti Dwivedi. In previous lectures, we studied about the IR spectroscopy, Raman spectroscopy. This is the another type of spectroscopy which we are going to study. It's about the rotational microwave spectroscopy. In this lecture or session, we are going to discuss some topics like theory of microwave or rotational spectroscopy, rotational energy levels, transition in rotational spectrum. We discuss selection rule of rotational spectroscopy, instrumentation and application part of the microwave spectroscopy. Now, first of all, what does microwave spectroscopy? Microwave spectroscopy is concerned with transition between rotational energy level. Transition between rotational energy levels in the molecule, and the molecules give a rotational spectrum only if it has permanent dipole moment. It means microwave spectroscopy are shown by only those compounds which have permanent dipole moment. For example, this is HCl and CO. Both have permanent dipole moment, so they are called as microwave active. They give the rotational spectrum. Another one is, example is H2 and Cl2. They don't give rotational spectrum and they are called as microwave inactive molecules. Rotational spectroscopy is only the second and the most important point is this rotational spectroscopy is really practically in the gas phase only. It is possible for gas phase, not for solid and liquid, where the rotational motion is quantized. In solids or liquids, the rotational motion is not quantized due to collision between their molecules, not quantized due to collision between their molecules. Absorption of electromagnetic radiation, it means the coupling mechanism. An electromagnetic wave is an oscillating electric field and interacts only with molecules that can undergo a change in dipole moment. And the oscillating dipole can be provided by the rotation of permanent dipole, like for example HCl, and this type of interaction leads to the microwave spectra. This is the direction of rotation of, and this is the direction of dipole, you see in this figure. Now come to the theory part or the principle of microwave spectroscopy. As we earlier discussed in my previous slide, microwave spectroscopy deals with the pure rotational motion of the molecules. In IR, both vibrations and rotations are observed. In Raman spectroscopy, both vibration and rotational levels are observed, but in this spectroscopy, only rotational motions are observed. So, it is the pure rotational spectroscopy, and the condition for observing resonance in this region is that molecule must possess permanent dipole moment. When a molecule having dipole moment rotates, it generates an electric field which can interact with the electronic component of microwave radiation. During interaction, energy can be absorbed or emitted, and thus the rotation of molecules give rise to a spectrum. Energy can be absorbed or can be emitted in two ways. That means transfer of energy can take place in two ways. First is absorption microwave spectra and other is emission microwave spectra. In the case of, first of all, this is your absorption microwave spectra. When there is a jump from lower rotational energy level to higher rotational energy level, that is transfer of energy from the incident microwave radiation to the molecule, then it is called absorption microwave spectrum. While the second type is emission microwave spectrum, when there is a reversion from the higher energy level to the lower energy level, that is transfer of energy from the molecule to the incident microwave radiation. A molecule can have three different moment of inertia, IA, IB and IC, along the axis of, according to their axis of rotation along the x, y and z. Moment of inertia, it is also called the mass moment of inertia, which is a measure of an object's resistance to changes in its rotation rate, and it is the rotational analog of mass. This is the case of HCl, where moment, this is IA along the x axis, moment of inertia along the x axis is represented by the IA, moment of inertia along the y axis is represented by the IC, and the moment of inertia along the z axis is represented by the IB. In case of HCl, we seen that along x axis along IA, moment of inertia is 0, while moment of inertia along the y and z axis are equal. According to their moment of inertia, rigid rotors are classified into 4 groups. Rigid rotors means it has only rotation, not vibration. Linear rotors, there are 4 types. Linear rotors such as diatomic or linear molecules such as HCl, OCS, acetylene and CO2, which have moment of inertia along x axis is 0 and along the y and z, it means IB is equals to IC. Along z and y axis, moment of inertia is equal. Second type is spherical top rotors. For example, methane, SF6 have 3 equal moment of inertia. It means along x, y and z, their moment of inertias are equal. Third one is symmetric top rotors. For example, ammonia, methyl cyanide and methyl chloride have 2 equal moments of inertia along x axis and along z axis. Moment of inertias are equal, but along z and along y axis, moment of inertias are not equal in case of symmetric top rotors. Fourth one is asymmetric top rotors. For example, water, methanol, vinyl chloride and formaldehyde have 3 different moment of inertia. It means along x, along y and along z axis, all moment of inertias are different, are not equal. They are not equal. On the basis of moment of inertia, there are the 4 main groups of molecules. As we earlier discussed in our slide, this is the case of linear molecule and this is the case of spherical top, where moment of inertia along the 3 axes are equal. This is the case of symmetric top, we will discuss in the previous lecture, in the previous slide, and this is the asymmetric top, where all the moment of inertias are equal, and along, this is along z axis, moment of inertia is more in comparison to along y axis and in comparison to along x axis. Important part, this is homonuclear diatomic molecules such as hydrogen, oxygen, nitrogen. it means H2, O2, N2 or Cl2 have zero dipole moment, that is they are non-polar compounds and have zero change of dipole moment during rotation, hence no interaction with radiation, and hence homonuclear diatomic molecules are microwave inactive. They are microwave inactive molecules, while heteronuclear diatomic molecules such as HCl, HF and CO, which have permanent dipole moment, that is they are polar compounds and the change of dipole occurs during the rotation and hence interaction with radiation takes place. Therefore, heteronuclear diatomic molecules are microwave active molecules. Now, we are now going to discuss how to calculate the moment of inertia of rigid diatomic molecules. A diatomic molecule can rotate around a vertical axis and their rotational energy is quantized. Assume a rigid, it means non-elastic bond. These are two atoms, these are center of gravity, distance between M1 and center of gravity is R1 and distance of the other atoms M2 between the center of gravity is R2 and total distance is R0. For rotation, assume a rigid or non-elastic bond where R0 is equal to R1 plus R2. For rotation about center of gravity C, M1 R1 is equal to M2 R2 or M1 R1 is equal to M2 R0 minus R1. In the same way, we can also calculate M2 R2 is equal to M1 R0 minus like this, or M2 R2 is equal to M1 R0 minus R2. With the help of these, we can calculate the value of R1 and R2. R1 is equals to M2 R0 upon M1 plus M2 and R2 is equals to M1 R0 upon M1 plus M2. Now, moment of inertia about the C is M1 R1 square plus M2 R2 square. Put the value of R1 and R2 from equation 3, which we have calculated in the previous slide. We can get the value of moment of inertia M1 M2 upon M1 plus M2 R0 square, or it is I is equals to, where this is the where this mu is your reduced mass. Now, a diatomic molecule can rotate around a vertical axis. The rotational energy is quantized by using the Schrodinger wave equation. The rotational energy levels allowed to the rigid diatomic molecules and are given by this equation. Rotational energy levels is equal to the h square, where h is Planck's constant, I is moment of inertia and J is the rotational quantum number. You know, this is your reduced mass, M1 and M2 are the masses of the atom and R is your internuclear distance. With the help of this, we can calculate the moment of inertia I. Now, we are going to discuss the energy levels of a rigid diatomic rotor or molecules. Rotational energy for a rigid diatomic molecule rotor is quantized and Ej is equal to h square upon 8 pi square j into j plus 1 in joules. While this is the rotational energy formula and it is calculated in terms of joules, while rotational energy is normally expressed in per centimeter. So, we have to convert from joule to per centimeter with the help of simple, you know, E is equals to h nu or hc into wave number. So, wave number of absorption you can calculate like this. With the help of this, we can divide this Ej upon hc to get the rotational energy in per centimeter. With the by solving, we get the simple formula. So, Ej is equals to h upon 8 pi square Ic into j into j plus 1 in centimeter inverse. This is, and where B and B is equals to h square and B is equals to h upon B is equals to h upon 8 pi square Ic, and this B is your rotational constant. Rotational constant. Now, we are going to discuss the transition observed in rotational spectrum. For the transition from j is equals to 0 to j to 1, since we have known this is the formula for rotational energy, Ej is equals to h upon 8 pi square Ic into j plus 1, where in this transition we can calculate from final to initial. In the next slide, we are going to how we calculate the value of j rotational energy level with the help of this simple formula. Ej is equals to b j into j plus 1. For j is equals to 0 to j is equals to 1, we have formula bj into j plus 1. Now, with the help of this simple formula, we can calculate the transitions between the energy level. So, delta Ej is equals to E j is equals to 1 minus E j is equals to 0. So, B into 0, so B into 1 plus 1 minus B into 0 plus 1, it means 2B minus 0. So, delta Eg from 0 to 1 is equals to 2B, or vibrational frequency is 0 to 1. For transition J is equals to 1 to J is equal to 2. Likewise, in the same way, we can calculate delta Ej is equals to E J is equals to 2 minus is equals to 1. Likewise, B into 2 plus 1 minus B into 1 and 1 plus 1 is equal to 6 B minus 2B, or it comes to 4B. For delta Ej 1 to 2 is equal to 4B, or this is 1 to 2, we get 4B. Like this way, we can calculate the transitions in the various rotational energy levels for another level. Since the allowed rotational energies are given by the formula H upon 8 pi square IC J into J plus 1, so we get this relation. The wave numbers of different rotational levels will be 0, 2B, 6B, 12B, 20B and so on. And for two adjacent rotational states, the energy difference is given by 2B. Hence, the wave number of the lines observed in the rotational spectrum will be 2B, 4B, 6B, 8B and so on, and the various lines in the rotational spectra will be equally spaced. Now come to the selection rule of rotational microwave spectroscopy. The molecule, the main selection rule is delta J is equals to plus minus 1. This is the gross selection rule, but the molecule should have permanent dipole moment or electric dipole moment, and the homonuclear molecules do not have pure rotational spectrum because they do not have dipole moment. Only heteronuclear diatomic molecules do have rotational spectra. Delta J plus 1 means for absorption spectra, delta J is equals to minus 1 for emission spectra. These are the allowed transition. It means transition takes place from 0 to 1, 1 to 0 to 1, 1 to 2, 2 to 3, but they are not from 0 to 2 or 2 to 4. These are not possible. These are the allowed transition. It must be in unity changes only. These are not allowed. These are allowed. Separation between the adjacent level is, we already discussed, is 2B, and B can be obtained from the spacing between rotational lines in the spectra of molecule. This is the rotational spectra of rigid diatomic molecules. Here from J to J plus 1, the selection rule is like plus minus rotational number. These are the allowed rotational energy levels of a diatomic molecules, and these are the transitions we are calculate in the previous slide, and this is simple rotational energy. this is the simple rotational energy is B J J plus 1. By simple putting, if for J is equals to 0, E J is equals to 1, on the basis of this equation, for J is equals for J is equals to 1, with the help of this formula, E j is equals to B into 1 plus 1, it means it comes 2B, and for J is equals to 2, E j is equals to B into 2 plus 1, it means 6B. So, rotational energy is like this 0, 2B, 6B, 12B, 20B form, but the allowed transition is from 2B, 4B, 6B, 8B, 10B, 12B respectively. Example of rotational of rigid diatomic molecule. This is the rotational spectra of HCl molecule, where value of B is 10 to the power 10.6. The line separation, you already know, you have line separation is 2B in each case. If it is given 21.2 centimeter, it means the line separation B is equals to 10.6 centimeter inverse. With the help of this, with the help of the formula of moment of inertia, with the help of rotational constant, we can calculate the moment of inertia and rotational constant of a molecule. These are the examples you can easily solve by going through the formula which I was discussed in my lecture. In this example, you have to calculate from the rotational spectra of HCl, value of B is this is the masses, and you can easily determine the bond length of the HCl molecule by simply putting in this formula. So, please try to solve with yourself. This is another example of calculation. You have to calculate the value of I and moment of inertia and interatomic distance of carbon monoxide, where rotational constant is given by applying the formula of I, moment of inertia. You can easily calculate the value of I and R. This is another example. You have to calculate the bond length of carbon monoxide using value rotational constant in this and reduced mass is this. By putting the formula, you can easily calculate the interatomic distance. Now, come to the instrumentation part. Monochromatic radiation of wavelength in the microwave region are allowed to pass through the sample. Instrumentation parts, first of all, this is the microwave radiation source. This is the waveguide through which the sample is passed. This is the sample cell, this is the modulator, and this is the detector. Monochromatic radiation of wavelength in the microwave region are allowed to pass through the sample space containing the sample in gaseous form. Now, the radiation are made to pass through the waveguide. After this, there is a quartz crystal detector which receives the radiation from the waveguide. After receiving the radiation from waveguide, detector vibrates and produce electrical signal which is amplified by the amplifier. After amplification, signal is displayed either as a recording on a chart or as a pattern on screen. Lastly, frequency or the range of frequencies of the detected radiation is determined by the pattern obtained on the chart or a oscillograph. Moment of inertia and internuclear distance up to this plus minus 0.0002 Armstrong can be calculated by changing frequency of oscillator and observing the intensity of transmitted beam. Now come to the application part of microwave spectroscopy. Microwave spectroscopy has been used for monitoring and control of industrial process, and it is the ideal process analyzer because of some qualities. It is non-invasive, it means the measurements can be made outside of the reaction chamber, eliminates the need of sampling or physical removal of the sample. Yani we can do the measurement outside the chamber. It can be used for dark colored samples. They analyze large sample volumes as microwaves diffuse out from the transmitter through the entire sample becomes lower. Microwave spectroscopy has been used in monitoring and control of industrial processes such as material with low dielectric constants such as plastic, glass, ceramics and composite materials can be easily determined with the help of microwave spectroscopy. Determination of moisture in various tobacco types can be done with the help of microwave spectroscopy. Monitoring of batch esterification reaction as in the esterification of butanol by the acetic acid. Monitoring of the drying process in industry as it is one that is hard to monitor. For example, huge cakes of wet materials when dried in big vessels can be monitored with the help of microwave spectroscopy. Other application, astrophysical applications, radio astronomy can be done with the help of microwave spectroscopy. Now come to the difference between the microwave and IR spectroscopy. Microwave spectroscopy, it is the characteristic of the absorbing molecule as a whole, while the resolution of the line is more in microwave and the substance under investigation must be in gaseous state. It is the most important. The spectra observed are nearly always absorption spectra, while in case of IR, the IR spectrum is the characteristic of functional group present in absorbing molecule. The resolution of the line is less in case of IR. The substance must be in solid, liquid or gaseous state in case of IR, and the spectra observed may be either absorption or emission, while in this case only maximum time absorption spectra appear. Now, in summarized form, microwave spectroscopy is concerned with transition between rotational energy levels in the molecule, and this microwave spectra or rotational spectroscopy, rotational spectra obtained only for those compounds which have permanent dipole moment. And microwave spectroscopy, it is a property of the molecule as a whole, and it is not possible to relate certain parts of spectrum to certain parts of the molecule. It is the property of molecule as a whole. It is not in the form of fragments. We cannot study the fragments of molecule with the help of microwave spectroscopy. The substance to be studied must be in gaseous state, and microwave spectroscopy is fundamentally not suitable for characterizing new compounds. It is one of the limitation of microwave spectroscopy. These are the assignments you can able to solve when you are going through my lecture. If in this problem, if you face any difficulty or if you have any queries, then you can contact me at my email ID. Thank you.